Okay, uh, welcome back. Now we shall start with the hands-on of the RNN session. I hope my voice is audible now clearly, and I hope the video is visible. I can see it on the streaming website. It is clear, so I think it should be fine with you guys. Thank you. Thank you for letting me know. Okay, so uh, in the last hands-on session we saw on we talked about CNN and how it works. Basically, the four same steps is going to be used here as well. In this particular hands-on session, we are going to look at two models of recurrent neural network. We would not explore into deep models like BI, LST, and GRUs. We won't talk about that. But the simple ones, we will talk about a vanilla RNN and how the output when you provide an input to the vanilla RNN, how the output is going to come like. We'll see that through an example too. Also, we'll see how the output looks like at the end of the LSTM network. We'll do this two exercises. Along with that, we'll see one implementation of we'll take a data set and try to implement RNN and LSTM into that data set. The data set is basically an ECG data set. It contains around 500 samples, so we are going to see that too. Right now, in this slide, what we need to focus is in RNN. Let's say if you have weights around let's say we have a weight W, right? So if you replace RNN with an LSTM, in that case, the number of weights is going to be four times the original weight that we had in vanilla RNN. So you have to be very sure about which one to use in which application. So RNN can be used, vanilla RNN that can be used, I think, in small data sets. If you have a sequence length of around 7 days, 8 days, like 7 or 8 samples, if you have in a sequence, then maybe you can go for RNNs. But if it's a long sequence, like let's say it's having 100 or 200 sequence length, in that case, you should go for LSTM. It allows you to forget the very past data, and it allows you to retain the recent data by making use of gating mechanisms that are inside of LSTM. Like LSTM has forget gate and input gate, and all those gates are designed in order to control the output, how it should look like, how much of the past data it should have, how much of the present data it should have. Anyways, the point is, LSTM can be used with very large data, and in that case, in which case RNN usually fails due to the vanishing gradient problem that I think was covered yesterday. And yes, the hyperparameters that we are gonna be visiting and with RNN or probably LSTM are these many. That is, you'll face that any type of if you are implementing it on Python, if you're implementing it on MATLAB, they will ask you the input size of the data, or input size while you're using a sequential network. Or maybe they'll ask hidden size, number of layers, batch size, and robot. You have to mention all these things uh, to get to set up the design or the architecture of the final RNN or the LSTM network you're working with. So how to decide that? Let's say you have a sequence data, and your sequence data appears something like this. So you have many samples. Let's say you have 100 of samples or 200 of samples. But right now I'm showing only two samples. Sequence length. By sequence length, I mean this particular part. That is, let's say this orange line is a sequence, or this blue line is a sequence. Then what are the data points that are contained in the sequence? That will denote the sequence length. And no, this is not the input size. Then again, what exactly is the input size? Here the input size will be this features or channels, the number of channels that you have. MATLAB provides you the flexibility to use any kind of sequence length. If, let's say you have a data set of let's say ECG recordings, and the first recording has a sequence length of 500, and the second recording has a sequence length of 600. So you can actually make use of different type and different sequence length in case of MATLAB. In case of Python, you can manually specify the sequence length. If there is not any, then in that case, even Python also takes into consideration the auto sequencing length. In which case, you can have variable sequencing length. That doesn't matter. But features and channels should be consistent in your dataset. So features and channels, the information regarding this, like how many number of channels that you have, that will come under the input size. So in this case, we have two features, or you can say two channels. We are using two sensors to pick up the data from our heart, and yeah, because of that, we have two input sides, right? And yeah, the next thing that you may come across is the hidden size. Now, hidden size is up to you. You can assign anything. You can assign a hidden size of 10, 20, 30, 40, 60. It is up to you. But how to decide what should be the hidden size in which case? Like let's say I have a similar fashion data. What should be the hidden size? If somebody asks what should be the hidden size in order to do a very efficient mode of training, then your reply in this case should be okay. If I have a hidden size of 2 or 3, it would work, right? But let's say if you have bigger data set, in that case maybe you'll need a lot of different hidden sites. Let's say you have a very stochastic data set, like let's say you have a biopotential signal data set. Uh, you can layer by layer distribute that signal into 32 channels, or maybe into 64 channels, or maybe into 256 channels. Likewise, you can decide your hidden size. Hidden size is basically it is including more and more depths to your original data. Okay, somebody is asking what is channel size here. Channel is basically let's say you have two sensors. You are collecting data from two sensors. One sensor is collecting one sequence, the other sensor is collecting the other sequence. That is basically the channel size. That two is basically the channel size. Right now you have two sensors, so the channel size will be two. Channels are basically how many number of features you have in your data set. And keep it in mind that the channel size, let's say your sequence is of length 700, then all your channels should have that 700 samples inside of them. Like in this case, our sequence length is 5. So both the channel 1 and channel 2 should have equal number of samples. It cannot have 4 samples, and it cannot have 5 samples here. In that case, maybe later on you'll face some kind of error in while training, because you're having something empty, And basically your RNN network or the LSTM network, it won't understand that empty, what empty and that is, what to assign to that empty. Should it be 0? Should it be 1? Should it be infinity? So it doesn't know. So that can create an issue. That is why, yeah, every channel should have the same sequence length, right? I think that should be clear. Let's say if you have 8 channels, in case of if you are making use of EEG uh, data, then in that case you may have 16 channels in your head, 16 sensors picking 16 different signals from 16 different positions. In that case, your channel size will be 16. Likewise, your channel size depends on how many sensors do you have to acquire the data. I guess that's clear. Anyways, the next hyperparameter that there is the is the is the is the is the hidden size. Okay, I think I talked about hidden size. Hidden size is when later on in the layers, how much more depth you want to look into. And the initially you had 2 channels. Later on, I want to see my if let's say I have a very stochastic data like EMG data. I want to see it more with more clarity. I want to use more channels to see to visualize the data. In that case, I will add up my I'll increase my hidden size. I'll increase that to 32 or maybe to 36 or 48. Depends on me how I want to how I want to see that data. Anyways, that is basically the hidden size. Let's say if you have the LSTM is the last output, is the last layer. In that case, what should be the hidden size? If the LSTM is somewhere in between, let's say like let me show you that block. If this is the case, you are giving some input and directly you are extracting the output from the LSTM block, right? In that case, what should be the hidden size? In that case, hidden size will depend upon how much output you want to see. If let's say you are doing classification, you will need only one output. In that case, your hidden size can be one. Let's say if you are making use of some sequence to sequence kind of regression. In that case, you can if you want to see three more future inputs, future outputs. In that case, you can make your hidden size with 3. When I'm talking about hidden sites in here, I mean the least amount of hidden sites that you need in your in your LSTM block. In this case, it will be 3. In this case, it will be 1. Fine. If you have, uh, if you have something like this, fine. That's configuration of the configuration or the design of the architecture of your neural network is something like this. Right. In that case, LSTM block could have any number of any hidden units that you want. But typically, for small data set, people usually prefer 52 to 64 hidden size. And for if you have a large data set, in that case, you may require a more number of hidden size. And also, if you have a very highly stochastic data set, when I say stochastic data set, it means highly random data set. Like biopotential signal, you cannot fix the trend of the data set. Uh, Data set like those. In that case, you may require hidden units or let's say hidden sites more and more, but probably in the range of 128 to 256. Anyways, this is how you design the neural architecture by RNN-based neural architecture. You take care of only input size and hidden size, and that's it. That's it for unlike in CNN, you used to have pooling operation. What kind of pooling operation you want? What kind of what kind of activation function you wanted. All those things you had to worry about in case of CNN. But in this case, in RNN, you only have to worry about the input size and hidden size. And that will depend upon your data set. Fine. The next thing that you need that you may come across is the number of layers. It is very redundant. This hyperparameter is very redundant. If you have a large data set, I'll go for three number of layers. If you have a small data set, then I'll go for one. That is the thumb rule to use number of layers. Then the fourth hyperparameter that you may come across is the batch size. Uh, Batch size is similar to what we have seen in case of CNN. In case of CNN, we saw that how to send the data, how to send basically our image data to the CPU or to the GPU. How do we send them? How do we send them so that the CPU can compute the data and then give out some result, right? So the same thing applies here as well. The sequence instead of an image going into a sample of image going into one of the thread of CPU. Here we send a sequence of data, and it goes in serial. It goes serially. Like the first timestamp data will go first, and the second timestamp data will go second, and then third timestamp data will go third. Likewise, they will go, but yeah, you can simultaneously send 32 datas at a time into your GPU. But that again depends. If you are making use of a GPU, then you can make use of 32 data at a time. If you are making use of CPU, I'd suggest that go for 12 or probably 16 data at a time. That will be that won't by doing so, you won't suffer doing other activities in LCP. That's a basic rule of yeah. You keep some portion of CPU out for maybe doing some other task. Yeah, that's how you decide what should be the batch size in case of any kind of deep neural network. Then the last thing that we may need to set is the dropout. How much dropout are we preferring? And in RNNs, in recurrent neural networks, you can take any RNN, you can take LSTM, you can take bi-LSTM, you can take GRU. In all those RNNs, dropout is a very crucial layer. In CNN, dropout won't mean much, but in case of RNN, dropout is going to mean much. Let me show you in a bit. I have to deviate from this presentation for quite that why we need dropout layers in case of RN too much, but in case of CNN too less. I'm opening MATLAB window. So I have opened my MATLAB window. Let me show you that. Uh, Here I will show you two things. That is why number of layers matter, and then the second thing is that why dropout matters. So let me open a quick example. Uh, See, the number of hidden units here is considered as 128, and I think we have not considered any sequence length. We are only considering the input size. There's no need to consider the sequence length. Uh, And here, if I go into the analyze section and show you how many number of parameters is going to be we will be training. You can see the number of total number of learnable parameters that you will be training at the end of this. You're only assigning 128 hidden units, right? But inside of them is there's something we call as A, B, and C. Basically, what happens is hidden state. The next hidden state is updated by a rule called as or a function which is given by the equation a h into a into h plus a into previous h plus b into current x, right? If we make you and this a and this b, they are basically matrices. A is a matrix of size number of hidden units into number of hidden units that makes it 128 into 128, and B is having a size of around 128 into 1 in case of RNN. In case of LSTM, like I told you before, it becomes four times that of vanilla RNN. So 128 into 4 becomes 512. So you can see this is a huge number. Because of this huge number, this total number of learnable parameters have become right now somewhere around 75,000. So every time if you are willing to train all the 75,000 parameters, then you'll need a high compute system. So what we can do is we can make use of dropout, and we can consider only 20 or 30% of the training parameter to be used. And in that case, what we can do is we can drop out 70% of the weight on which the data is very accurately trained, and we'll focus on the 30% of the weights in which the data is not that accurately trained, and then we'll train them. And finally, we can come up with all those parameters trained, we can say equally. So all those 75,000 parameters trained equally. So that is why dropout in this case matters much, but in case of that CNN, we don't usually worry so much about dropouts. Only if you are having a lot of channels in your CNN layers. In that case, only you have to go for dropout. Unless and otherwise, you don't need that much. The other thing that I wanted to show you is that if you copy it, let's say if I copy this one, let's take another one here. Then we join this here, this here. Let's okay, this is 128 again. Fine. So let's analyze for this now. That was 75,000. Now this is 3 times that of 75,000. And you can see that now the previously, because our input was only 12 channel data, so we were only training 512. We were only training weights like 512 and 12 in that time. But now we have to train 512 into 128. We have to train from the previous layer, right? So here I have used number of layers is 2 in this case. In the previous case, the number of layers was 1. That is why I was telling you that if you have a small data set, then probably go for low number of layers. One will do just sufficiently as compared to. Fine. Let's come back to our slides. Okay. So yeah, that's basically all the hyperparameters. Now let's see how are we going to implement code using Python, because most of you guys will not be having a MATLAB tool. The legit version of the MATLAB tools. That is why we are going to show you the demonstration in the Python. And let me tell you something about the data set. ECG, we are taking the ECG 5000 data set from Kaggle website, and this data set is containing 500 sequences. When you'll go through the information about this data set, they may say that they have 5000 sequences in their data set. But when you download the data set and you check for yourself, then you'll find out that there are only 500 sequences. So yeah, the data set ECG 5000 is currently containing 500 sequences, and then each sequence is having a sequence length of around 140. Sequence length won't matter much. And then the third thing that is there is that they have considered they have acquired the data using one sensor only. That means we have only one channel here. So the first thing that we need to look at is the input, right? I'll again break down. Are all sequences of same length? Yeah, all the sequences are of same length in this case. But you can use variable length sequence. It doesn't matter because I showed you. Nowhere do you have to specify the sequence length in as a hyperparameter. Right. In case of Python, they may ask a sequence length sometimes, but yeah, that's you can go ahead and put it in the auto mode. In the auto mode, it will consider any sequence length that you're putting into. Okay, so we're dividing this into four families. So the first step is considering the input, right? So you take the data set, and you make them into a format we call them as deep learning format, DL format. And if you're stuck at some point, let's say you are using CNNG or you are using, whatever kind of network you are using, let's say you're stuck at some point. You want to see that your data is going into your data whether your data is going into the model correctly or not. In that case, what you can do is you can quickly go into Google, and you can Google out what should be the DL format, deep learning format, for this particular model, whatever model you are using. Right now, since we are talking about RNN and LSTM in Python, they accept this as in this format. The first tensor should have batch size, the second tensor should have sequence length, and the third tensor should have input size. These are the dimensions, basically. We can say it like in the case of image, you have x and y coordinates, right? In this case, you don't have x and y coordinates. You have only x coordinates. You have only one sample of data. The y coordinate in this case will be the sequence length. Fine. And then the coordinate will be the batch size. Batch size meaning that how many samples. In this case, let's say if you are taking two samples, the batch size is two, let's say. In that case, two of the sample, let's say sample number one and sample number two, will come together into your model. That is the meaning behind all this. Sequence length, it can vary. Sequence length could have 140 time steps. It could have 160 time steps. It doesn't really matter. Input size matters. Input size you have to keep same as that of the channel size that you are considering. Right now, our channel size is 1. That is why our input size in this case will be 1. So in this case, if I want to consider, if I want to process two data at a time, then I will consider batch size as 2. If I want to consider the whole sequence, then I will whole sequence. It doesn't matter. The sequence will already be, if you put your sequence length in auto mode, then in that case your sequence, the entire sequence is being considered. So the sequence length won't matter. Sequence length is just to check whether you are on the right sequence or not. The third thing that will matter is input size. So in this format, you would have to keep your you would have to arrange your tensors, right? So this will make a 3D tensor in which the first dimension will have two data. The second dimension will have the sequence length of the data. The third dimension will have the input size. In this case, one. Fine. The same thing in case of MATLAB. In MATLAB, we don't have tensors. Rather, we have matrices. So in this case, we'll have a three-dimensional matrices, and the first dimension will be linked to the features. That is one, and the second dimension will have the sequence length. That is 140 in this case. The third dimension will have the batch size. Let's say we want to provide four inputs at a time. So we'll give here four, right? So in case of MATLAB and in case of Python, these things are different. Then the third thing that we need to ensure before training, before sending our dataset into the model, is that we need to split that dataset such a way that the training dataset is devoid of the testing dataset. The training dataset doesn't contain any samples from the testing dataset. Because if your testing dataset is containing some samples from the training dataset, then you are essentially training on the same dataset and testing on the same dataset. In that case, what will happen is basically your model is already trained with the dataset. So you'll never know if your model will work or function properly in a real life scenario. Are you getting me? So that is why you need to separate your testing dataset from the training dataset. And in this case, you can make use of standard format, that is 7 to 3, or maybe you can use some for you can keep some for validation during the training while the training is going on, and you can do so by splitting them into 6 to 2 group. Now, this is the code behind all the input behind what we are doing during the input stage. We are basically taking in the ECG 5000 dataset from UCR UE dataset function. This dataset is already imported in some library. I'll show you later on. Now, this thing is important here. Right now, I want to do classification. Right. So for classification, your data type should be in the format of int64. Let's say if you're willing to do some regression problem, or maybe maybe sequence to sequence regression you want to do. In that case, this needs to be np.float32 again. I'll show you. In a quick review, I will show you how to change your current network, your classification network, directly into a regression network. Later on, I will show you. Don't worry about that. Right now, let's focus on this training testing split. There's a command for it, train test split, in which you can specify your test size. This is nothing. This is some random state. This is to shuffle the data. You can put anything here. 42 is just the standard notation, but you can put anything here. You can put 0, you can put 1, 2, 3, or you can put any integer value in here, positive integer value in here. And then you need to specify the input data and the output corresponding to that input data. Fine. So once you're done with this, then this function will automatically generate the split. It will do the split for you. It will give you xtrain, xtest, and then it will give you the output training data and output testing data. Then the next thing that I also told in the previous class is that we need to convert this data set. Whatever the data set we have gotten here, we need to convert them into a tensor. Why? Because we are making use of PyTorch here, PyTorch library. Now, PyTorch library has inbuilt functions that work on tensor dataset and not on NumPy dataset or array dataset or matrix dataset. it will work only on tensor dataset, not just PyTorch. Many of the deep learning frameworks that we are using, like PyTorch or TensorFlow or something, probably something else, all of them are making use of tensors. So I'll recommend that whenever you keep this part of code fixed, every time you need to train on new data set. Fine. So you can put you can convert them into tensor, and then you can convert them, you can flatten them, and to flatten them you make use of the view function. And basically in this particular piece of code, what we're trying to achieve is that we are trying to convert them into the format that we talked here. This format: batch size, sequence length, and input size. Finally, the tensor should have the first dimension of the tensor should have the batch information. The second dimension of the tensor should have the sequence length information. The third dimension of the tensor should have the input size information. I think that's clear, and that we can do by making use of this particular line of code. Fine. Once you have done this, done all of this, then you need to load that data set. You need to create a data store for this of all these tensors, and you have to because every time you're sending in 64 data set, 64 data samples, right? So you have to create a data store in such a way that in each iteration you're sending in all the 64 data set at one go. So that is basically sending all those data. You're specifying here the batch size information, and then you're providing you're telling that, okay, group them in that manner, so that it will become 64. It will accumulate all the 64 data at a time and then send them together. So this is what does that. The second thing is the second thing we need to look into what we can do with the LSTM. For this particular data set, yeah, it's wrong. It should be 500 for this particular data set. Since we have around 500 samples, I would suggest that go for 50 bed size is sufficient if you are having a GPU. In case you are working on a CPU system, then batch size of 32 or 16, whatever is available with you, that is doable. Because this is not that big. The length of sequence you can see only 150 is there. So this is not that big, but let's say if you're making use of if you are working around with the bioinformatic data set, you have a genomic sequence. In that case, you may have one sequence length of around 1400, 14,000 or 15,000 length. In that case, maybe in that case, maybe you will have to bump up this batch size, and also the hidden size in that case should be reduced. Yeah, so you can tune them, but for this example, you can take a hidden size of 32, 16. It is doable. Number of layers is one is sufficient, and then input size is basically the channel information. Channel information is one, so we would consider one. Dropout you can have you can vary that between 0.2 to 0.5, but usually for big data set, we for if there are too many learning parameters, we consider taking 0.5, and if there is too less training parameters, in that case we can consider 0.2 or 0.1, like that. Okay, so the next thing that is there with LSTM is that setting up optimizer and the LSTM architecture. In the CNN hands-on session, we also we looked into this, right? So basically here we are defining that, okay, let's take cross entropy loss because it's classification. We are doing classification, so we are taking cross entropy loss. If we had two classes, then in that case we could have taken binary cross entropy loss. Let's say if we would have like data like let's say we want to do regression kind of thing. In that case, you can make use of RMSE or MSE laws, whatever there is for regression. So here you can use the you can change the loss function optimizer. I'd say that if unless you have your own optimizer, I will say that go for the default settings. I will not change them too much. And then you define your LSTM architecture. So basically, your input will be taken by the LSTM. Your input X is being taken by the LSTM. Then it is being stored in the out variable. Then this out variable is being flattened in this piece of code, and then that flattened is being considered by the fully connected network. Basically, at the end of this, you'll have I think you'll have 32 into because the channel size is 32, hidden size is 32. You'll have the input as 32, and then yeah, you'll have the information about their classes. So all those things will be reflected after we process the entire thing. Fully connected network, you have to keep in mind that the number of neurons in case of fully connected network layer will be the same as the number of categories. Let's say you have 5 labels or 5 classes. In that case, uh, you'll need to assign that the output number of neurons should be 5. The input number of neurons will be automatically adjusted, or maybe if it is not it is not being automatically adjusted, then check the last LSTM layer that you have used, whatever the hidden size you have used there. Let's say the hidden size is 32 there. Then the input to the fully connected layer should have 32 neurons. And this fully connected layer is finally gonna produce the labeled data set, labeled data. Then this labeled data can be later on used by the cross entropy loss function to basically compute the loss, and then it will do all the pair propagation things. I'll show that in this particular piece of code. Yeah, so just like case of CNN, we are sending in data in batches, and the model is training them and storing the results in PRED variable. And then we are considering all the PRED variable, and we are considering the Y-based data, and then we are computing the loss function loss from that, and then we're storing it in loss, and then immediately we are saying that okay, make all the gradients zero right for now, because if you don't do this piece of code, then the gradients are going to be accumulated, which will cause a problem during your training, and which will give faulty results. So make sure that this is always there just after you have updated your loss information. Then do the backward propagation. While doing so, update the different parameters, the different weight parameters inside the LSTM, and maybe inside the fully connected layer. Change all those weights, and once you're done, then yeah, do it for the n number of iteration for all the epochs, or until all the epochs are completed. Once that is done, once your model is trained, then you can go for evaluation of that model by using this particular piece of code. Don't worry about the code. I'll show you, and I'll also give you later on this code so that you can work it out. I have already uploaded the CNN code for you to refer. Now, the next thing I promised you that I'll show you how to quickly change from RNN to LSTM and LSTM to RNN. So yeah, basically you change this name. Here you have LSTM, change it to RNN. That's it. That's all you need to do. Nothing else. You don't have to worry about anything else. Also, number of layers Yeah, you can consider removing that because RNN doesn't no, RNN never takes number of layers as an input, so you can remove it. It doesn't matter. So by doing this one change in your code, you'll be getting the results from LSTM network. Or probably if you are in LSTM, then you'll be getting the results from RNN network. Getting me? So I think this part is clear. Now let's execute some code. Uh, okay. I guess you can see my window here. Uh, I am history. So I'm inputting this particular function. That is why I need to do this installation. It won't take much time. Okay, it is connecting to the runtime. Yeah. In the morning session, somebody asked me how to see whether you're using CPU or GPU. Here you can see this exclamatory sign. This exclamatory sign is basically being used to tell Collab that okay, I'm commanding mm, to your base environment right now, I would say that to the PowerShell right now. So if you want to use if you want to check the profile if GPU is working or not, you can do so by making use of this one. This exclamatory sign followed by NVIDIA hyphen SMI. That you can do, and yeah, you can check whether the GPU is being used or not. The next thing that is there is let's just quickly run the code. Once I have shown you, let me check whether this is for RNN or LSTM. Okay, this is for RNN. I'll quickly show you how to move into LSTM, and then I'll show you how to change. Right now, this is doing classification, right? This is making use of this particular piece of code to classify things. Later on, I will show you by changing three things only, you can change this classifying network into a regression network. Only you have to change three things, and then you'll be able to change it into a regression network. I'll quickly do it, then I'll train it. Okay, so the loss is decent. It is around 2.366. It is not that good, but yeah, it's doable. You can evaluate it later, but just for sake of you, let me show you. Yeah, 89% accuracy on the ECG dataset. Now let's quickly do LSTM. Now let's some of you want to use LSTM right away. Then all we need to do is change this line. Hopefully it is easy for you. I'm not seeing any comments that is everybody getting this? Let me know if it's getting difficult or if it's easy. Some kind of feedback will be helpful to me as well. Then let's check the accuracy. Accuracy of LSTM is also 89%. So I think we did great. 89% is a decent accuracy. Not very good, but for now, as a tutorial, I think This is doable. Now let's quickly change to show you to make this into uh, a regression network. First thing we need to see is that the output is having only one dimension. In this case, the output was having 5 dimensions because there were 5 classes, right? Uh, to ensure that, what I will do, yeah, and this here, I will change this to 1. Or maybe if I'm making use of LSTM, let's use LSTM. Uh, I can change this to 1. And the third thing that you need to do is you need to change the loss function. Fine. So we changed 3 things: the loss function, and here we change the output layer, and here we changed it to float 32. Yeah, I tried it before, so I know this because int64 is going to give you an error because regression output could be floating variables. That is why you have to specify this data type. Okay, so by doing this 3 changes, I think we can rerun the code and I can show you. There will be some errors, but they won't be something that would concern us. We'll still get the regression output. Accuracy is a little bit low, but yeah, you get it. We are getting regression output now. So likewise, you can convert from classification to regression, and then maybe you can do maybe if you want to do sequence to sequence regression. In that case, you only have to specify here like how many number of sequence do you want. If you want 3 or 4 sequence, then you have to specify here that many output. Likewise, you can even change from one from LSTM code to RNN code, RNN code to LSTM code. If you want to do classification, you can do classification. If you want to do regression, you can use the same piece of code, change 3 places. I told you those 3 places. If you change it, then it will get converted into a regression problem. If you want to do sequence to sequence regression, in that case. Like if you want in your output sequence, in that case you only need to adjust this only this parameter after doing MSC loss, after changing the MSC loss and the data type of the output. So yeah, that's all. I think I have covered RNN LSTM in 1 hour of time. If there is any doubt, you can go ahead and ask me in the comment section. I'm checking. If you want to see the output from one single RNN or one single LSTM, I did do a homework just before this lecture to show you how it looks like. So yeah, you can see here the results. I considered a random some input. I took one sequence, only one data set. The time step was 3, and the features, the channel size was 4. And then I deliberately selected the hidden size to be an array of 2. And yeah, then I directly checked what would be the output. Since it is considering some random weights in the beginning, that is why you are getting this kind of output, and this will be the output from RNN. Let's say you want to, let's say if you want to check information regarding your network. Let me quickly show you. One way that you can do check this, I can show you here. We have to install, I think, a new. Let me look it. G4. This comes in handy if you want to really examine how your data is passing through different layers. In that case, this comes in handy. Let me show you how to check all those layers. So, yeah, sometimes Copilot comes in handy as well. Yeah. See that the parameters, the number of weighting parameters that we have right now is somewhere around. It is having a matrix, and the matrix dimensions are somewhat around 480. And then the the fully connected layer, it is having 33 parameters. And likewise, if you multiply all those parameters 4 into 480 plus 33, then I think that will come out to be 4513. Yeah, this is a good way to check whether you're going great or not. I don't think that this is matrix. It should be number of parameters. Yeah, this is number of parameters. This is saying 4480 and not 4,480. Anyways, I think this should be sufficient. In any case, if you have any kind of doubt, you can go ahead and ask me. Uh, I'm following through your comment section throughout the session. Is there any doubt? Hello? No. Okay. Don't have any doubt. Let me stop sharing. Okay, fine. So if there is no doubt, then we can wind up this session, and then we can start again at 5 o'clock. I think Prof is going to be late, so maybe today we'll be starting at around 5:30 or somewhere around that. I'll let you know through the WhatsApp if there is any change in plans. In the meantime, mm, yeah, I'll upload the codes so that you can follow through. Shall I wind up the session? Okay.